So, yes, I work at the University of Southampton, and our research there really is in energy management of computing systems. And that's down to kind of Internet of Things, very constrained devices, and some of you may have seen our demos of self-powered IoT over the last few days. But today I'm talking really about how we manage mobile computing systems. And I appreciate I'm in an HPC track here, and clearly there's words in there that may resonate with HPC, but I should start with a proviso. There's probably one or two slides that are directly targeting HPC and what I'm talking about today. But what I'm going to concentrate on really is the outcomes from an EPSRC program grant that's coming towards a close now. This was the PRIME project, PRIME standing for Power and Reliability in Many Core Embedded Systems. And it started out really with this aim that you can see at the start, and that was 5 or 6 years ago, seeing a progression in the number of cores that we'd expect on mobile chips, and the obvious problems with what that was going to do to power consumption and energy consumption. And we could spend a lot of time arguing about what we were aiming to get to, or what the big vision was here, but I think we were looking at systems where you may be expecting kind of HPC-like systems in a mobile platform, where we had a significant number of cores that we were trying to manage. It was a consortium made up of a number of different universities and industrial partners that you can see there. And the basic aim, or the approach we took, was considering a cross-layer system where we've got our applications executing on our hardware. And the main bit really that we were concentrating on in the work package that Southampton was leading was the runtime management that sat alongside the operating system. You think of it as your kind of power governors working with your scheduler, with your mapper, trying to manage the resources that we had available to us. To give you kind of a nice visual example of what we were trying to get at, this is an example from early on in the project. And so there's a video is going to play in a second on the left-hand side, one using one of the standard Linux governors on demand, and then one using our kind of lightweight machine learning approach. As this plays, on the right-hand side here, you can see the frame rate we get. The blue line is our approach. The green line was this baseline, and then the power consumption down the bottom. And the kind of thing you can see here is the video at the top is lagging behind the one at the bottom. That's because for these first few seconds, it was exploring all of the different choices that it had in the DVFS levels that it had available to it, making some bad choices and therefore dropping the frame rate. But after about 5 seconds, you can see that it pretty much keeps up with the on-demand approach. In fact, if you get rid of the lag between the two videos, most of the troughs that you see on our approach line up with the baseline approach. The nice result here, it's a bit hard to separate the two traces, but the green trace is effectively the upper envelope of our approach, which is switching around between frequencies a lot more. And this translates to something like a 20% reduction in the energy consumption, or if you look at it the other way, a 20% improvement in the battery life of your device. This was executed on a single core, but it's kind of a starting point of where we were trying to move from. It was using a very simple machine learning approach, reinforcement learning, nice and simple. Kind of works in the same way that you might consider us to learn. So you're in a particular state, and you have a whole load of actions that you can take. And to start with, you're exploring that space. You try an action, see what happens, and then either get a reward or a penalty, so learning whether or not it was a good or bad thing to do. And so over time, you build up a table of what are good actions for particular states that you're in. We also looked at applying this to temperature. PRIME was about power and reliability, and really we looked at reliability from a thermal reliability perspective. And so similar kind of approach, but this time instead of power driving or energy consumption driving the reward or penalty, it was thermal models of aging. And so at the beginning here, it's exploring the space. It's making some good and some bad decisions. And I can't skip through the video. Okay, if the video is to carry on in time, you end up with a reasonable steady state where the blue trace there is 25 to 30 degrees lower than the red one. Again, this default Linux approach. There was a slight loss in performance. It was in the order of 5 to 10%, I seem to remember. but giving quite large improvements in the thermal reliability, or the modeled thermal reliability of that system. So that's kind of where Prime was coming from. And obviously, in the limited amount of time I have here today, I can't tell you about all the different things that we did. But what I wanted to concentrate on was kind of some of the key avenues we explored and some of the challenges that we were looking at overcoming. So first of all, we started out thinking of a kind of system like the one I've just showed, where you had a single application running on your single platform. And that's kind of nice from a research perspective and how you can constrain the problem, but quite a lot less relevant to a real system you might expect. If you consider a mobile device in your pocket, it's not executing the same application continually. Applications executing on it are changing, and if it's a multi-core device, it's going to also be having concurrent workloads executing on there. We also looked at kind of the trade-off between online and offline characterization and modeling of the system. Again, you can get some quite nice results from pure offline characterization of these systems, but if you think that we were looking to kind of apply this technology to something where there are thousands of different devices it needs to execute on, or within systems that it can execute on, thousands of different applications, and if they're executing concurrently, state space is going to explode even more. So we have to find a balance really between what we can do in a lightweight manner offline with what we can then explore and leverage at runtime. Also, the example I showed a minute ago was a single core approach. Looking at many core, we needed to scale this up through multi-core platforms and also exploring what might be possible in the future. And one of the kind of guiding principles of what we were doing is we did actually want to experimentally validate what we were doing here on real platforms. Okay, so one of the things that we noticed kind of leading on from those early examples was how the workload changes during execution. So even within this is again a video decoder at the moment, even within that video decoding, there's quite a lot of variation in the workload as you get different frame types appearing. And so we could manage that by instrumenting the video decoder so it knew what the frame type was, and that affected the state of the system. But if that same video decoder was then to run a different video, different resolution, different frame rate, that workload would change again. And obviously there becomes a point where you're over-instrumenting the application that you're trying to manage. So how do we detect these kind of step changes in the workload that we're experiencing? Then you may stop executing those workloads, change, and execute a different application altogether. And that's going to see a complete change in the workload that you're trying to manage. You need to be able to detect that this has happened, because if you've learned really well how to manage a video decoder and then you load up a web browser, if you're applying all of that previous knowledge to the web browser, you're going to be making completely wrong decisions. So how do you know that you need to do something different? And then, as I said earlier on, how do we cope with different threads executing in parallel in the system at the same time, contending for the same resource? So in terms of detecting the workload changes, we looked at a number of different methods for doing this. A particular one shown here is a statistical divergence approach that identifies when these kind of workload phases have changed, when there's a dramatic change within the workload that's going to cause us to need to relearn how to best manage that system. So at that point, we can then, in the case of the Q-learning approach I showed you earlier, refresh our table, clear it out, and start again. So our application's running, the workload changes, or there's a change within a workload. This gets detected. It resets the table and starts re-exploring the state space that we're operating within. And once it's learned, it can then exploit that information and carry on executing. But for many examples, so like the video decoder where we switch to a different video, completely wiping all of the knowledge that we've learned is a bit of an overreaction. And actually what we want to do is do very similar things, but we have to just kind of modulate and adjust the way that we're doing it. And so we looked at how we could transfer some of the learning from this table that we built up, from the knowledge that we'd learned over time, and adjust it to fit new scenarios. So this is kind of the basic approach of Q-learning. You start in a pure exploration phase, trying all the different options. Then at a certain point in time, you start to exploit some of that knowledge as well as still doing a bit of a learning. And then ultimately, you've got all the knowledge you need and you're just exploiting it. And so what we looked at is, well, if our workload changes altogether, it's completely different. There's nothing that we can gain from the table we already had. Then we just go back to the start here and start exploring again. However, if there's some knowledge to retain, we can skip back a step. We can continue to exploit some of the knowledge, but we can also explore some of those parts of the table again, rebuild up the knowledge that we had. And so the results at the top here are an application executing. At a point in time, the workload changes. It detects this, and the first thing it does is it scales all of the information it has. It realizes that the workload is higher, so it scales all of the outputs in that table, and then starts the process of doing a bit more learning, filling in the gaps. And you can see the blue ones here are the optimal actions to take, and you can see that it adjusts slightly, but that knowledge has allowed us to learn what to do and to make the right decisions a lot quicker. That was a complete online learning situation. It didn't know anything about the system beforehand. It didn't know anything about the right and the wrong approaches to take. That worked quite nicely for power. You can get quite quick responses on different decisions that you're making, and you can learn quite quickly what's good and what's bad. For the thermal properties, that was a real problem because the effect of making a change and seeing what its impact on temperature was has a much larger time constant. And so to learn the properties of that system takes a period of time that's going to inhibit what your application is actually doing. So we looked a bit at offline methods as well. This is a system where we were doing image filtering, and we could do the image filtering either in hardware on FPGA, either through the DSP or through the CPU. So we had a heterogeneous platform to operate on. And we did an exhaustive search, effectively, of the operating points within that system. So all the different frequency levels, different core counts that we're enabling on the CPU, and we could get a plot of the energy per frame against the performance. And so in this case here, if you wanted very low frame rates, it was most efficient to do it on the CPU. But after that, the Pareto front's kind of shared by the DSP and the FPGA. For the other workload, it was never worthwhile doing it on the CPU. It was off the top of the graph here. But then the DSP and FPGA kind of allowed you to explore that space. Then at runtime, we can build surface models of this, and then we can navigate that model to identify the operating point that we want to operate at for the most efficient operation point for a particular performance level. This was very offline heavy. You'd need to do this for every application and every combination of applications running on it. So we looked at how we could kind of handle this concurrent execution of threads, and also on a system like a big. LITTLE system where we've got different resource available. And it was finding a balance between that offline and online phase. So here, offline, for each individual application executing in isolation, we looked at all the different mappings that could be made onto hardware at the highest frequency, so not exploding that state space too much. And then at runtime, we look at all the applications that want to run, what the performance requirements of them are, and then picking the thread mappings that minimize energy while meeting that constraint. And then because all of this was done at the highest frequency, we then need to work out how to optimally scale DVFS to execute it. And so we had an offline characterization of the memory reads per instruction, so how memory bound or compute bound a workload was, and therefore what frequency was best to operate that at. And so we then picked the highest frequency to operate that at in order to save the power. And you can see the results down the bottom here. I think the red and the green ones are the on-demand and conservative that effectively just ran at the highest frequency. And our approach, when the memory reads per instruction gets higher, when it becomes quite a memory-bound workload, it pulls down the frequency to avoid unnecessarily waiting. In the interest of time, I'm going to have to move a bit more quickly, but we also looked at extending that approach to HPC systems. So we considered non-uniform memory accesses in calculating this kind of memory-bound value. And we evaluated that on both the Xeon and the Xeon Phi. Quite an interesting comparison between the two because the Phi has a single DVFS cluster for all 61 cores, whereas the Xeon allowed us to have individual DVFS adjustment. The approach compared to baseline Linux gave us quite considerable energy savings, and compared to some of the state-of-the-art approaches that have been reported, we got a nice improvement in energy efficiency and actually performance as well. And not quite as nice as the Isambard system that you saw earlier, but we've towards the end of the project now, we're exploring with a 27 8-core big little cluster to look at how we can scale some of these approaches. We also looked at taking the kind of offline model building approach that you saw earlier on and looked at how we could use this on something like the Phi. So this is a stereo vision application exploring all 61 cores at all the frequencies that they're operating at. We can get that same kind of surface response and then use these same gradient descent approaches to navigate this space at runtime to minimize our energy consumption for the workload that we want to execute. Okay, my last couple of slides, just 2 open source tools that I want to tell you about that have come out of the project. So the first is if you're interested in research in kind of runtime management approaches, one of the things that we struggled with quite a lot was actually how you get off the ground in implementing and comparing these different systems. So we've released a framework for this, which is effectively a set of APIs that allow you to implement your runtime and interface with the application knobs and monitors and the hardware knobs and monitors as well, and allow very easy comparison between different runtime managers. And the other one that we have, you may have seen Matthew Walker's poster on yesterday, but he's done a lot of work in online power modeling, power prediction, providing very stable models of power consumption, even if you don't have physical power sensors on your chip. Okay, so to conclude, we've done a lot of work really looking at runtime management that I've only been able to touch on here, kind of exploring this story through from managing single applications up to multiple and currently executing applications, trying to find this balance between online and offline approaches, and looking at how these things can scale as core counts increase. I didn't have time to talk about it here today. We've also explored kind of novel platforms as part of the projects as well. And there's a variety of tools. If you're interested in, you can explore a bit further. Thank you very much.
We have time for 1 or 2 questions.
So, quick question. It seemed like in the online example, you were trying to detect a change of application, when many times that would be a decision made by the operating system scheduler. Is there a reason, were you avoiding that, or was that just a detail we didn't see, that the scheduler wouldn't collude with you and even store your machine learning and restore your information when it reschedules the same thread and that sort of thing?
Yeah, so one of the decisions we took quite early on in the program is that we didn't want to get into kind of re-engineering and forking things like the scheduler. We wanted to try and work alongside it as much as possible. I think your point's quite interesting, though. We could have pulled out some of the information from the OS on when applications were changing and what were changing. But that only helps you with when the application changes. It doesn't help you with changes within an application. You do get these quite considerable changes during a single thread or single application execution, where actually all of the knowledge you'd learned up until that point doesn't really apply to what's happening anymore.
I have a question. So in your online energy efficiency analysis, did you consider a fixed threshold for your thermal breakdown for aging effects, or?
So this was on one of the early slides, was it?
Yeah.
So this was using models of thermal reliability for mean time to failure, both due to temperature peaks and also cycles.
So you used a constant for the whole analysis, or did you try weighting it?
Constant
for mean time to failure, the thermal reliability metrics. So did you experiment with varying the mean time to failure expectations?
So we weren't trying to optimize execution to meet a particular lifetime.
Okay.
We were trying to manage execution to minimize the thermal effects, so maximize the mean time to failure.
Let's thank the speaker. Thank you.